Okay, so the best way to try when you're trying to do okay, we have four boxes, each with a different color: white, red, blue, and orange. There may be a prize in one or more of these boxes. We know the following facts. There are exactly two boxes among the boxes that are not white. That means among the red, the blue, and the orange boxes, they do not have a prize. One do not have a prize. That means that exactly one that way, but since we already used the previous color sheet, competition, one that we talked about, then we may be able to. But for the first part, it's not really necessary. If the blue box has a prize, then the red box has a prize. If the orange box does not have a prize, then the red box does not have a prize. The orange box has a prize, then only if the white box has a prize. So, what boxes have a prize? How do you solve this problem? Let's assume that something happens and seem to arrive at a contradiction. If you assume that something happens and you don't arrive at a contradiction, that does not necessarily mean that it's true. Why? Because if you suppose that something is true and you arrive at truth, you haven't proven anything. Why? What did you prove? That P implies true. And P implies true is always true, no matter what the value of P is. That is very important. You should always remember that. If you suppose that P is true and arrive at true, you haven't proven anything. Because what you proved there was P implies true. And P implies true is always true, no matter what the value of P is. So then what are the boxes? Orange and white. Why? Yeah. So then, if and only if. So then, once you conclude that the orange has a prize, conclude that the white one does. How do you conclude that the orange box has a prize? Mhm. That only one has a prize. How do we know that that one is the orange one? Do we just guess? Okay, so now we know that only one among the red, blue, and orange boxes has a prize. How do we know that that one has to be the orange box? So, and then that would be a contradiction. Okay. We're going to assume that the orange box does not have a prize. Then, if the orange box does not have a prize, the red box does not have a prize either. But if the red box does not have, now, what do you conclude about that? If the red box does not have a prize, then, no, then because of the contrapositive, if the red box does not have a prize, the blue box does not have a prize either. That means that the three of them, orange, red, and blue, do not have prizes, which would be a contradiction because it says exactly two do not have a prize, not all three. So then you would arrive at a contradiction. The only thing we assumed was that the orange box does not have a prize. Therefore, the orange box must have a prize. And since the white box has a prize, if and only if the orange box has a prize and the white box has a prize too. We could have done it like this also. Assume that the blue box has a prize. Then the red box has a prize. That's a contradiction because we would have two that do have prizes. Then we would know that the blue box does not have a prize. Now, now we would have to prove it again. Now, if the then I could once I conclude that I could say, oh, but then the since exactly two do not have a prize, and then it has to be blue and orange or blue and red. But because using the same logic that we used before, we could arrive at the conclusion here. If the red box does not have a prize, then the orange box does not have a prize. And again, we would end up with three that don't have a prize. Okay, how do we do that formally? Let's remember what we did last class. Last class, we talked about this. I'll give you the solution here. I'll upload this afternoon so you can see it. We defined the new function 2 out of 3. And now using 2 out of 3, we can do this. There are exactly two boxes that do not have a prize. That means 2 of 3, not R, not B, not orange. If blue box has a prize, then so does the red one. We translate this as B implies R. If the orange box does not have a prize, then the red box does not have a prize. Not O implies orange box has a prize if and only if the box has a prize. Okay, now that's the, how do we do this? We're going to assume that O is false. So my hypothesis, what I have is not two of 3, not R, not B, not O. Not O implies R, not R. B implies R. I'm going to suppose not O. By exercise 1.1, which we did, it means that R is not equal to not B. By the definition of XOR and applying another rule, I skipped a step here. It means that equal to B. By the definition of not equivalence, is not R is equal to B. Modus ponens 4, not 4 and 6. Six and 7. Modus ponens 6 and 7. I get, oh, with this one. Oh yeah, 4 and 6. The order is not right, but then if I have not R, I can conclude not B. And if I can conclude not B, then replacing 6 and 7, I have B, and I arrived at a contradiction. I'll write that on the board. Not using this, but not using what I wrote there, but using this. here it is. It's not modus ponens 4, 4 and 2. If I have not O by supposition, and I have that not O implies not R, I can conclude not R by modus ponens of 4 and 2. Right here. Now, modus tollens of 5 and 5, of course it's not 5 and 5, but I have not R is equal, here I have modus tollens. I have B implies R, and modus tollens of 7 and 3 gives me not B. Now I'm going to replace, I don't know why those numbers are all messed up. I replace not B, here I have not B is equal to 6 and 7. I have not R is equal to B. That means that not B is equal to R. No. Not R is equal to B. Then I have B. And here I can conclude not B because of not R. There. Modus tollens and not B is equal to R. That I can conclude here. Not R is equal to B. That means I can replace not R for B here. So I arrived at not B and B. Let's go through it again. The reasons here are wrong. But then I supposed not orange. By exercise 1.1, if not O is true, I know that only one of not R and not B have to be true. This is equal to saying not R equals B, which is equal to saying not R equals B. And then modus ponens, it's not 4 and 6, but it's modus ponens of 4 and 2. I get not R. Now I know that not R is equal to B. Then I can replace not R for B here. Not R, no, modus tollens, I have not R, and I have. If I have not R, and I know that B implies R, I know that not modus tollens, I have not B. But I have that not R is equal to B. Then I conclude R. So I'll write it This is exercise 1.1. If I know that exactly 2 of P, Q, and R is true, and I know that P is true, then I know that exactly 1 of Q and R must be true. So this is exercise 1. So if I have this, now this would be, if you want 2 of 3, I can write it in any order. I can write it here. Which is the same thing. So I have 2 of 3, P, Q, R, and I have P. If I have these two, 1 and 4, exercise 1 apply to 1 and 4. I will know that exactly 1 of not P and not R has to be true. That means not R is not R, exclusive or not B. Now, we know that P XOR Q is equal to not P equal to Q. This is the first definition of XOR. We have that. Now, we have a definition. This is applied to 5. This is 7, 8, 9, 10, 11. Okay. So now we have not R, this is applied to 6. This is the definition that not P equals Q is equal to not P equals Q. This is another negation of equivalence. Now, notice components of 2 and of 4 and 2. Notice components of 4 and 2. This is 4 and 2. Modus ponens of 4 and 2 gives me not R, which is this one. Now, negation. So now I have C implies R, and I have not R. Modus ponens of 8 and 3 gives me not B. Now, I have not R, and I have not R equals B. That means I can replace B for not R. Replace 7 and 8. Now I have, in 9 I have not B, and in 10 I have B. That gives me a contradiction. The only contradiction I had was, the only supposition I had was not O. So that means that O must be true. The rest is just replacing. I hope that those numbers are right there. I have not R, not B, not O. This is the definition of 2 or of 3. I have that O is true. If O is true, it means that not O, that. I have not true. I replace O for true everywhere, and then I have not R, and not true is false, right here, and false or false is something, or false is that something because of identity of or, and I have not R and not B. Now I have O is equal to B, so O is equal to W, then I can remove W, and I have not R and not B, I have O and W, and finally I have O and W and not R and not B. This is the kind of thing that you would be asked in an exam. I'll upload the solution, I'll fix the numbers. The only mistake is the numbers there. So we'll have that. Okay, now. Now we're going to start talking about quantifiers. If we don't finish talking about quantifiers, I'll upload the presentation. I'll take it and you can watch it offline. Since we don't have class on Thursday, although the new syllabus did take that into consideration. But then you can, if we can't finish our presentation, then you can watch it on YouTube. Okay? So. Did you read quantifiers? No. Yeah? It was quantifiers for today. So. I haven't uploaded my presentation. I'll upload it later on. I'm still looking at last semester's. We're going to start to talk about quantifiers in the general sense, not in the particular case for logic quantifiers, but in the general sense. You will see that this has more of an application when we start talking about induction, although when we talk about logical quantifiers, the you will see some applications, but not that much. So then let's just start talking. Why would we use quantifiers? We use it when we have binary operators like sum, like and, like or, like times. Also, a binary operator to which you could apply all of this would be maximum and minimum. You could apply it also. So you have an associate operator, let's call it star. It's associative. What does it mean to be associative? It means that x times or operated with y operated with z is the same as putting the parentheses around x and y. It's commutative. It means that x operated with y is equal to y operated with x. It has a neutral element or an identity. That means that x operated with u is equal to u operated with x equals, and that equals x. We have the addition, the multiplication, conjunction, and disjunction. What would be, although you already saw, what would be the neutral element or the identity of the sum, of the multiplication, of the conjunction, and of the disjunction? False. Why? Because P or false is equal to P and true is equal to P. 1 times x is equal to x, and 0 plus x is equal to x. You usually don't use these same symbols. Instead of a sum, you use a sigma, a capital sigma. Instead of times, you use a capital pi. Instead of and, you use like a backwards a. And instead of or, you use a backward e. Of course, this is for all, and this is exists. Now, what does it mean when I operate something like this? I'm going to operate over all x's that make q true, but I'm not going to operate over the x itself. I'm going to operate over e, which is an expression that depends on x. Let's look at examples. Let's say I want to add all numbers, all, here I should have put all integer numbers between 1 and n, and I want to add the square of I. This is a new notation for something that you had already seen before, right? Which is a summation for I equals 1 to n of I squared. You had already seen that. You should already have known how to manipulate these types of expressions, but then you can do it easily with them. We have the following inference rules: substitution and two types of Leibniz. No matter if no matter what happens, you know that you can always, if you substitute z for p in a quantified expression, you must substitute it both in the range and in the body of the simplified expression, of the quantified expression. Now, if p is equal to q, it means that I can replace q for p in the range of the expression. Now, it's I can also replace it in the body, but you can do something that is much more constrained. If E, it's you can if P is equal to Q, you can always replace it in the body. But if E implies that P equals Q, then you can also replace it in the body. I'm going to explain this one, which is kind of difficult to understand. First substitution. I want to replace N for, for N in the quantified expression. You have to make sure that P, I'm replacing Z for P must not contain X. For X does not occur in 4 nor in N, so then I can replace N for 4, and it would be, I replace N for 4 in this expression and in this expression, and it says summation of I equals 1 to 4 of X plus 4 squared. That would be one substitution. Now Leibniz. I know that X plus X is equal to 2X. Then I can always replace it in the body here. X plus X is equal to 2X, and I replace it there. Now, let's say I want to do the following. X is between 1 and N, and I want to say absolute value of X plus, and I want to add all the absolute values of X plus 2. Since X is greater than 0, because of the range here, then I know that I can replace X for the absolute value of X. Then I can replace this one for X here, because the range here implies that the absolute value of X is X. Now some other examples. These are axioms regarding quantified expressions. If I am operating something, all of the x's such that false over P, that gives me the unit or the neutral element or the identity. If I want to add all prime numbers that are greater than 2 such that they are even, and I want to add x to the 10, that would give me 0. Why? Because there are no prime numbers that are even and that are greater than 2. Then this is false. Then this would be 0. If this would have been a multiplication, then this result would have been 1. Now, if I want to add all numbers that are greater than equal to 1 and less than or equal to 0, and I want to add x to the 10 of all the numbers that make this predicate true, that would be 0, because there are no numbers that make this true. If I want to do it with 1, the same thing. Now, I want to see if there is a prime number, if there is an x such that x modulo 3 is equal to 0, and I want to do that for all numbers that are prime, greater than 2, and even. Since this is false, then I have to have the identity of or, which is false. Since this is false, I need to have the identity of and, which is true. Okay, so this is, if the range is false, then the result, no matter what the body is going to be the identity of the corresponding operator of the quantifier here. Now, 1-point rule. If x does not occur in E, and I want to operate over all of x's that are equal to E, and I want to operate them with P. Notice that there's only one element that makes this true. Then I have to replace E for x in this expression. For example, I want to add x to the 10 for all x's such that x is equal to 3. This would be 3 to the 10. Now, I want to see x a natural number such that x is greater or equal to x and less than 4. There is only one number that makes this true. Why? Because x is a natural number, then only one. Then this would be 3 to the 10. Now, is there an x equal to 4 such that x modulo 3 is 4? Then I just replace 4 for x, and I would say this is equal to saying 4 modulo 3 is 1. And for all, it would be the same value because it's the 1-point rule. Now, these are axioms, so I don't have to prove them. So I'm just going to show you why. I'm just going to justify why they are true. I want to show that they can distribute. I'm going to operate using E1 over all x's that make R true. I operate that with the result of operating E2 over all x's that make R true. This is the same as operating x E sub 1 operated with E sub 2 over all x's that make R true. Let's look at it this way. Notice that in this case, I can apply distributivity when the range is the same for both of them. The range is the same here, and it's the same here. So I want to compute the sum of the squares of all numbers between 1 and 3, all integers between 1 and 3. And I want to add it to the result of operating. That means the result of adding the cubes of all numbers between 1 and 3. So then, what would the result of this be? It would be 1 squared plus 2 squared plus 3 squared. What would be the result of this expression? It would be 1 cubed by plus 2 cubed plus 3 cubed. Now, since the addition is commutative and associative, I can write it out like this. It's 1 squared plus 1 cubed plus 2 squared plus 2 cubed plus 3 squared plus 3 cubed, which is in fact the summation of x squared of all x's between the summation of x squared plus y cubed of all numbers between 1 and 3. Quite easy, right? That's distributivity. This is not a proof, it's an example. You can't prove things like this. I'm just justifying it with an example. You don't have to prove it because it's an axiom. You don't even have to prove it because it's an axiom. Okay? But I'm just showing you why it's true. For logic operators, the quantified expressions are always well defined. And that would mean that if for all x's such that make R true, then E sub 1, and for all x's such that R, then E sub 2, it's the same as saying for all x's, if R, then E1 and E2. And the same thing for exists. If there exists an x such that R and E sub 1, or if there exists an x such that R and E sub 2, then I know there exists an R such that E sub 1 or E sub 2.
How do we know if some expression is not defined?
Oh, it's well defined if I don't have things like a division by 0, or if I don't have things that are infinite, if I have all numbers between that I can't compute, something like that. But mostly if I have a division by 0, something that has an error, that's what it means. But in logic expressions, they will always be well defined. Sometimes in summations they can be ill-defined, but not here. Okay. So now range split. Range split, when we have range split, we have the same body, but different range. Since it's an equality, I can do it from right to left or from left to right. But then I'm going to, again, this is not a proof, but it's just a way to justify why things happen. So I want to operate with the same operator, all with the same P, all x's that make R true and all x's that make S true. Now, this is the same as operating all with P, all x's that make R or S true, and I operate it with all x's that make R and S true. Now, I'm going to use these equivalences. If I have that x is a number, an integer number between 1 and 4, and x is a number between 3 and 6, it means that x is a number between 3 and 4. Do you understand that? It means that, let's see if I can. Well, the scale isn't right, but I'm sorry. It isn't right. That's all. If I have x is between 1 and 4, it would be this top line. X is between 3 and 6, it would be the bottom line. If I want it to be true for that this is true and this is true, then it's the intersection. It would be that x is between 3 and 4, right? Now, if I have an or, it would be, if it would be an or, it would be the sum of the two lines, and it would be all of this. It would be from 1 to 6. Okay. So once I explain these two equivalences, then let's go on. Now, the sum of integers between, I write them this way, but they're the integers between 1 and 4. It would be 1 squared plus 2 squared plus 3 squared plus 4 squared. Now, this would be 3 squared plus 4 squared plus 5 squared plus 6 squared. Now, again, I can group them any way I want, and I would have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 3 squared plus 4 squared. Now this, because of equation 2, would be the summation of all x's such that x is between 1 and 4 or x is between 3 and 6 and the squares. And this would be, because of this equation here, the summation of x's between 1 and 4 and 3 and 6. This is just an example to justify the rule. Disjunctive range split. Now this is a bit harder to understand, but we have the following. What happens if I know, what would happen if these two were disjunct, that they didn't have anything in common? Then, if not R and S, what does it mean when I said not R and S? It means that R and S is equal to false. Then, when I do the range split, I don't have to worry about the intersection. So, how do I prove that? I prove it this way. Because of range split, when I operate things with the same body and different range, it's the conjunction of the range operated with the disjunction of the range. Now, if I know that not R and S is true, it means that R and S is false. Then I replace R and S for false. And because of empty range, this is the identity, and the identity operated with this gives me only operating with the or. This is a very powerful axiom. Well, it's not an axiom, it's a theorem because I proved it, and you can use it, and we'll be using it later on. Now, this is harder. If the operator is idempotent, like and or, then you can forget about the conjunction as well. But here I'm using a lot of theorems that you should be able to prove on your own, and I'll leave them as exercises. Okay. So, range split. I start with operating all p's such that R, and I operate that with the result of operating all p's over X such that S. Because a range split is the operation with and with or. Now I have this theorem, add this to your list of exercises. P or Q is equal to P and Q or P XOR Q. So then we would have to prove that. Add that to the list of things with practice, practice, practice. Now, I'm using another theorem here. I'm saying that R and S and R XOR S are disjunct. That means they can never be true. They can never be both true. Another theorem that you should prove. And since it's the disjunctive range split, then I have it here. I just split them like that. Now, since it is associative, here the parentheses are around these two. Now I'm going to put the parentheses around these two. Now, since this one is idempotent, these two, then I can just replace this for this here. Now, disjunctive range split. Once again, since this is not true, I can replace this. Since these are disjunctive, then I can replace these, this. I can just add the disjunctive range split and put both of these in the range of the quantified expression. And using this theorem again, I see that R and S, or R XOR S, is equal to R or S. So R and S, or R XOR S, is equal to R or S. And there I proved it. Of course, I still haven't proven two things. I haven't proven that P or Q is equal to P and Q or P XOR Q. And I haven't proven that P and Q and P XOR Q is equal to false, which is what you have to do. More axioms, which are dummy interchange, which is that if I'm operating X over R, and inside the body I have a quantified expression that operates Q such that all Y such that Q operating with E, I can exchange R and Q if X does not occur in Q. Nesting, if the quantifiers are well defined and I have for all X and Y, well, I'm operating over X and Y, operating with R and Q, and Y does not occur in R, I can leave R alone here with X, and I put another quantified expression with y. Dummy renaming, I can rename if y does not occur in y, I can replace, I can use another variable. I can use y instead of x. Change of dummy, if y does not occur in r or e, I can replace x for a function and then quantify over y. We'll see an example of this, of change of dummy, in the next slide. Let's say I want to add all natural numbers between 0 and x, but I don't want to add I want to add x plus 2 for all numbers between 0 and 10. That would be the same as adding all y's between 2 and 12. In the first case, I would add 0 plus 2 plus 1 plus 2 plus 3 plus 2 plus 4 plus 2 until 10 plus 2. That would be 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12. Now, there's another condition here, which is f has an inverse function. So f of y is y minus 2, and the inverse function is f of x is x plus 2. Now, I'm adding the numbers that are between 0 and 10. Change of dummy, x is f of y is y minus 2. That means that x is, that I have to change it for y minus 2 here and y minus 2 here. Now, y minus 2 plus 2, that will give me y, but here it's operators over these types of over inequalities. I add 2 on both sides, and I get 0 plus 2, y minus 2 plus 2, x plus 2. This gives me 0 plus 2 is 2, y minus 2 plus 2 is y, 10 plus 2 is 12, and y minus 2 plus 2 is y. And you get that. Although these are things that you already knew how to do before, right? These are simply things that you did when you were working with summations and with other things. Okay, now let's start with this. Oh no, it's not this one. Oh yeah, it's this one. Now let's see how this applies to logic quantifiers. So I'm going to sort of skip over. You should have read this, I think. So we'll finish looking at this later on, but now we don't have, when you have predicate logic, you have to have predicates. Predicates are functions whose value is true or false. So if an elf, any elf, commits an action that is a misdeed, then he is an evildoer. Rumpelstiltskin is an elf who kidnapped children. Kidnapping is a misdeed. Therefore, Rumpelstiltskin is an evildoer. Okay, so you have to define a predicate. A predicate is something applied over elves in this case. Evildoer D. D is an evildoer. Commits DA. That means D commits an action, which is A. Misdeed A. A is a misdeed. Now I have constants. R is a constant that represents Rumpelstiltskin, and K is a constant that represents kidnapping children. Now, how do I translate that? I say, hypothesis, I say, if an elf, when I say an elf, I'm not saying a specific elf, but I'm saying any elf commits an action that is a misdeed, any action that is a misdeed, then he is an evildoer. Then I would write it like this: for all D, if for any D, elf, for any action A, and for all this D shouldn't be here. For all D and for all actions D, if D commits A, then and A is a misdeed, then ED is an evildoer. My assumption is that R commits K and K is a misdeed and R is an evildoer. Now we have another thing here. We have some other things here. The thing is, I'm sort of already talking about how you translate, which isn't what I wanted to do, but we can just go on and see how we can do this. Now these are another one. In an island, there are two types of inhabitants, alphas and gammas. Inhabitants can be only of one type, not both. A terrible tragedy killed off but one alpha. Inhabitants that have three eyes are alphas. Gammas can fly. You meet two inhabitants, A and B. A has three eyes. You conclude that B can fly. Why? Because there's only one alpha. And alphas have three eyes, then you can then you know that B can't be an alpha. It has to be a gamma. Then it can fly. Inhabitants are alpha or gamma or not both. Do you translate? For all H inhabitant, alpha H if and only if, or X or gamma. And you can also write it like this. For all H, if someone isn't an alpha, then if and only if it's a gamma. Only one alpha is left in the island. Now, I will leave it like this, and because this is the way you translate there exists only one. You translate it like this. There exists one, which would be this one, and for all others, which aren't X, then they can't be alpha. This is the way you translate there is only one. Sometimes you write it like E, well, there exists, and an exclamation mark, but that doesn't exist here. You would have to write it like this. There exists one X, which is an alpha, and all other X's are not alpha. Or you could also have written it for all H's that are alpha, though they must be equal to X. Inhabitants that have three eyes are alpha. That means for all inhabitants, if it has three eyes, then it's an alpha. Gammas can fly. If H is a gamma, then it can fly. Our assumption is 3 and A is different to B. Why is it different? Because I met two of them, then it must be different. And the conclusion is that it can fly. Now, witches can be good or wicked, but not good and wicked. Witches with wings are good. Witches that have brooms are wicked. We can conclude that there are no witches with wings that have brooms. And these are the translations. These are the equivalences, and then next class we'll look at this in more detail, and we'll start seeing what we can prove, okay? Now, we'll end this class here, unless you have any questions, any problems with your labs, anything? A quiz?
Yeah, but
And what?
one of the cognitive tests was very long and stressful. I went to the office, to the teacher's office, the other Corla professor, and he couldn't finish it. So
You couldn't finish it? Then what is this for? And you paid for this? Did you pay for the or no? No?
No, but that wasn't. Yeah, that wasn't before this, but after we printed, we have a bad grade.
Did you try to do it by cases? No, it seems that this would be a good case to do something by cases.
Si es que yo creo que para eso que para
So we're doing by cases. P equals true, P equals false. Now, if P equals true, it would be Q equals R equals true equals R. This would be Q equals R. There we have it. Now, P equals false. It would be here P false. It would be that P would be false. False equals false. 3 lines. You would always try, when you see that something is that long, you would always try and do it by cases. And not cases, cases is sort of like a truth check. No, it isn't, because I'm only doing it with what? You do it by cases. But then you understand how easy it would be doing it by cases.
Yes.
It would be true, true, Q equals R, Q equals R, false. This would be false. This would be false, false is true. Then I would have to prove that this is true, which is false, false. Did you have to do it by actions? No. They just told you to do it, right? Always try and prove things. If you get stuck, you didn't read proving the golden rule, which is difficult to prove. And one way I proved it was by this. It is one of the presentations that I left for you, right? And one of them was by cases. And I do it with only one. Here I have P, Q, and R. I just use my letters to rewrite things. Okay?
Wow. Thanks.
You're welcome. Did you have to pay for that? I did. Awesome. I don't care if I solve one of your complex exercises. Okay.
Uy, es que yo mucho ese libro, pero es que solamente resolvimos lo de la derecha. Ni siquiera resolvimos lo de la izquierda. Lo primero que hicimos fue transformarlo en una cosa de la agregación.